Should I start? Hello. Hey, guys. Good afternoon in Pacific time. I guess it's good night in India and other places where people are coming from. Thank you for joining us today. It's been a pretty amazing last couple of weeks. We announced the GA of Flight 2. But a little bit of going into that before that, my name's Ketan. I'm the CEO and co-founder at Union, but also the guy who built Flyte long time ago at Lyft. And over the last few years, we rebuilt Flyte with Flight 2. That's what we GA'd a couple of weeks ago. And there's been a lot of enthusiasm about it. Thank you. Today, what we'll do is we'll go through the journey of why we rebuilt Flyte, what it is, and most importantly, we think it defines a new category. We call it the durable AI runtime. AI runtime is probably maybe okay understood, where you can run models, agents, and the data stuff that you need for doing all your AI training or agents and inference. Durable is a very interesting word. And what I'll try to do is, as we go through the presentation, we'll try to arrive at a common definition of the word durable. All right. Before we get there, let's get to how we got here. So I think I have touched this in a previous presentation, but I'll kind of reemphasize it. Orchestration is what we did after we built the first piece of software. The moment you build a piece of software, you want to connect it with other pieces, because a simple program on its own is almost not as useful. The people have done business process automations, shell scripts, make files, and all kinds of things to do orchestration. But in about 2012, Airflow and other products were in open source, and they were used for ETL, and they were all the rage. And in 2014, we started thinking, oh, we need to do more than ETL. We have these business processes, like when you're doing a financial transaction or moving data between services, you need microservice orchestration. In about 2016, 2017, I was at Lyft, and we were facing a different challenge. We had teams of researchers and engineers working together to get machine learning products into production. And oftentimes, infrastructure was a huge challenge for them. That's what led us to build Flyte, which we open sourced in 2021. And it was donated as part of Linux Foundation. And thank you for all the community who has adopted it and the love that it has gotten. But over the last couple years, we saw new use cases emerge on the platform, as well as we saw the age showing up on the platform, right? It's been 10 years old, things change. And that's what got us thinking of what the next 10 years of AI runtimes look like. And that's how we ended up building Flyte 2. But Flyte 1 exists, and it is still in production at many, many companies. I'm sure all of you have used at least one model or an inference that has run on Flyte. More than 4,000 companies exist in the ecosystem and downloading them consistently. And it scales amazingly well in production. But it does solve, it's very much focused on one problem, and that is machine learning, training, and model development. But as we started looking at the new workloads that were coming onto Flyte, we observed that infrastructure failure was actually a common problem for most developers. And remember, when our first thesis with developing Flyte itself was the rapid iteration that is required and infrastructure problems that people had to scale their ideas to production. And oftentimes, the successful teams were the teams that actually were able to scale rapidly from an idea to a production scale. And for that meant taking away the problems of infrastructure provisioning, as well as failures that are caused because of various infrastructure issues. And yet we see today that most of the tools that exist are unable to solve the infrastructure problems. They are mostly focused on code replay, which is, I think, a very, very important problem, but it's not all of it. And I'll tell you why. Like, I think if you take examples of common issues, because so many workloads are containerized or running on different nodes, and we have GPUs, and we're running in cloud infrastructure where failures are common. Failures are not one time, they are like happening all the time. For example, if you're using Spark machines, they get preempted. If you're using GPUs, the new GPUs need burn in time, or sometimes they just don't work. Networking craps out, or sometimes you load a lot of memory, use a lot of data, and you run out of memory. So a lot of these issues are essentially infrastructure failures, and they're hard to recover from. And we are seeing more and more workloads are becoming longer and longer running. Everybody knows it takes like forever to train an LLM. Like, I don't have to tell that. And then now reinforcement learning is even getting longer running. In fact, agents are also run for a long period of time. There is a benchmark that measures the time for which an agent runs, or is able to hold up one line of thought, right? Now take that as a scenario. An agent is this non-deterministic process that's continuously changing, twisting in its decisions, and picking and running things differently. And an infrastructure failure happens right in there. For example, maybe it was doing deep research and it runs out of memory just because it was trying to pull some data. What do you do? This is where it becomes very, very expensive, because recovery today in these cases is extremely manual. You have systems that would fail, and then it would page you at 2 a.m. in the night, and your agent has now failed. Let's say it was going for 18 hours and it failed at that 18th hour. What do? You get up in the night. The only solution oftentimes is write some YAML, deploy a Kubernetes job, fix something, and really no recovery. So you restart from beginning. So you have two penalties. I don't want to be an engineer who gets woken up at 2 a.m. So that's one penalty. And the second one is that you're computing it again. So that's like, and compute is becoming way more expensive, especially with GPUs and all the things that we are doing today. So these two penalties really become extremely expensive in production. And we think for any team that is even going from an idea to production, any decent scale, will encounter these problems again and again. And so to resolve these problems, you need a system that goes beyond simple code replay. It is able to resolve and fix infrastructure issues dynamically, or aid the human very quickly to fix those issues. And this, we think, is a new category of a system. This is the AI runtime. And so in this diagram, you'll see that the central part is called the AI runtime. Let's not focus on that a little bit. Let's look at what's above it. We have these amazing long-running AI workloads, which can be training, batch inference, real-time inference, agents. And we have an extremely complex infrastructure setup. No single company nowadays is one cloud. You're multiple clouds. There are many, many companies that are exploring different silicons, different GPUs. We already had ARM and x86. We have now different types of GPUs and TPUs. You're running containers and clusters and Kubernetes clusters. It's getting extremely complex. A non-infra aware orchestration system in between just simply schedules tasks and is unable to resolve from issues. This is where, if you could fuse in the infrastructure as context and really build a truly dynamic orchestration engine, we think it could solve most of the problems. And for that, that's what Flyte 2 is. Flyte 2, if you had to take three things out of it, is a durable execution engine. It's able to automatically recover from things like out of memory, preemption, node loss, um, along with other things that we'll show in a little bit. It is completely dynamic. And when I say dynamic, it's kind of a word that's used very loosely by many people, but it is dynamic in the sense that it can actually write code that it can dynamically use to schedule new things. And this is truly dynamic in the nature. There is no predeterminate DAGs, or a DSL here. It's a fully dynamic execution engine with durability built in. So you can now write loops, branches, try catch, recursion, async IO. You can do, and not only in Python, you actually have a Rust SDK as well. And finally, when we were building these systems, we realized most of the people who were running large scale evaluations or backtesting and inferencing, they prefer Flyte. And so we wanted to make sure that batch inference is it's one of the best platforms to run large scale batch inference on the system, which durably. But many times you also want to run real time inference on the platform. You want to expose reports, ideas, views, build Streamlit apps, and serve models. And agents, we believe in the world, are going to use SLMs to essentially solve the problems in real time. And real time inference is that's why under the same roof. To dive, sorry, but whenever you introduce a new system, I think oftentimes the question is why one more system? So let's try and look at where we stand. I think it's fair to compare to two of the top contemporaries in the world at the moment. Even though it's not Flyte is not really a workflow engine at its core, it's more than a workflow engine. But it's we should compare to workflow engines because that's where it many times gets compared to. Airflow, it's great for ETL, as we've said. It was built for ETL, and it's static DAGs. There's no dynamism. You don't really generate code. It cannot handle error. It doesn't understand any infrastructure and doesn't really scale containerized workloads dynamically. But it's great for ETL. So if you're doing ETL, you can stick with Airflow. We think it's if you're doing anything with AI, Flyte is better. Second one's temporal, and temporals actually needs careful comparison because temporals, I think the way they brought the word durable execution to the core, and they do a fantastic job with it. But what temporal is a code replay engine. So let's take an example. Let's say you were doing a big agentic job where maybe you were accessing data from some data warehouse and the agent was analyzing it. Accessing that data was probably millions of rows, let's say. It would blow up your memory because you had scheduled. In the case of temporal, it would find the failure and you'll have retries on the activity, and so it would rerun that activity. But rerunning a infrastructure failure doesn't resolve the failure. It just results in the same failure again, and you pay the cost twice. This is where you need something like Flyte that actually can recover from those issues. Before we go ahead, though, I think so. I hope you see the differences with like Flyte and temporal. I think just the one line statement over here is that durability is more than just code replay. It's code and infrastructure replay, and Flyte is one of the only runtime systems that actually is able to bring this and help you navigate these new age problems that are happening with agents. To talk more about this and our design choices, I hand it over to Niels. If you want to learn more.
Awesome. Thanks, Ketan. Hey, everyone. My name is Niels Bantilan. I head up the AI ML team here at Union, and super excited to talk and share more here. So let's go ahead and I will share my screen. So to understand where we're going with Flyte 2, Ketan's already set up a lot of the context here, but I just want to hammer this home. If you remember, the pre-GPT era, before the 2020s, Flyte 1 was really born in this era of Python 2.7 to 3.5. Type hints were super nascent at this point, if not non-existent in 2.7. The async await story in Python was not mature either, as well as the container story. If you recall, getting the right CUDA versions and the right container versions and lining it all up was basically dependency hell. On top of that, back in 2018, when Flyte was first built and architected, Kubernetes was also at 1.10. It had version 1, but there were no managed K8 solutions, and gRPC was also kind of immature. And this kind of led us to prioritize scale and safety at this time when data ETL and machine learning training and batch workloads were super important to get right and to get to completion. This led us to build a DSL, a domain-specific language. And so what you had to deal with if you have ever used Flyte 1, or if you're not super familiar with it, there was a DSL that allowed you to compose these workflows into static DAGs. And you had to deal with promises that were our own take on promises, dynamic workflows, which you had to kind of do some gymnastics to get right, and our own conditional syntax. And so there was quite a steep learning curve when it came to building these workflows if you were not familiar with these kinds of tools. The point here is that this was the right set of decisions back in 2018, but now in 2026, we think these are the wrong constraints, and so that's why we set out over this past year, culminating in our launch last week, to build and launch Flyte 2. So without talking your ear off even more, I just wanted to jump into a quick demo. I'm actually going to show off the Flyte 2 dev box, which is a fully fledged Flyte cluster on a K3s cluster that can run locally, but on my DGX Spark machine. So I got a DGX Spark a few months ago. I use it for, I would say, maybe half of my LLM serving needs, as well as it's my home lab setup with a Flyte cluster set up on there. So I use it to do small experiments, run kind of LoRa fine-tuning experiments, as well as just serve the latest smaller language models. So Qwen 3.8, 27 million has been running on there for the past few days. The thing I really want to show before jumping into the code here is that we can take an idea from local to a GPU, if you're lucky enough to have one, in a few minutes. And on top of that, the code works locally and remotely, and there's very few code changes you have to make to actually get that done. And if you want to get started even more quickly, we have a TUI if you're into TUIs as opposed to browser-based UIs, and you get live logs and reporting. So I'm going to show all of this over here. I'm going to hop into my VS Code editor, and just to show that I have a GPU here available, this is my DGX Spark machine that I've SSH'd into. And the first thing I'll show you is just plain Python. We're claiming that this is pure Python, so I need to prove to you that this is pure Python. So here I just have a very simple script. I have a function that has a slope and intercept that's hard-coded. It computes the y, given the slope input x and an intercept. I'm just going to map over that value over a range of values. So again, this is pure Python, so no magic going on here. I'm just printing main. Where Flyte comes in, I've already pip installed it into my environment, is I import Flyte. I define a task environment, which I name. I'll lowercase that. And then what I'm going to do is decorate these functions with @env.task. Now, these are synchronous functions. Flyte 2 actually also supports async natively, which I'll show you a little later. But I'm just going to run this, and I just ran it as a simple Python function. Nothing magical is happening here. But when I do this, I can initialize from config, and I can start introducing a few Flyte concepts in here. So I'm going to do Flyte run. I pass in the function I want to run with its inputs, and I'm going to print out the run URL. And what I've actually done here is I've configured this to run against a local dev box that I have set up here already. So I ran this earlier. I have a dev box running at localhost 380. This is the UI that I'll take a little deeper dive into in a second. But I'm going to go ahead and just run the exact same script. And you notice these are happening sequentially. So that's kind of funny. We're talking about parallelized execution with Flyte and scale. we're not introducing extra magic here. So the way Python behaves is the way Flyte behaves. What you can do to auto-parallelize this, and actually this will just use a bunch of async machinery under the hood that's abstracted away from users if they don't want to interact with async. I just replaced this regular map call with a flyte.map. If I run this, you can see now these are all running in parallel with some concurrency limits, right? And that ran a lot faster. So this is the UI. I can actually run this on, let's say, way more elements. You can see here, the UI no longer shows a DAG, right? As we said earlier, there are no more DAGs and no more static workflows in Flyte. Everything is a dynamic execution graph. And I may cancel this since there's a lot of executions this has to plow through. But as you can see, this is all running concurrently, just using the flyte.map construct. I'm just going to abort this run. And just to hammer the point home here, everything is just a task that you can compose together. So I can take this Y list and I can do something conditional here. Ketan's going to show you later in his demo how this hooks into infrastructure as context, makes things durable at the infrastructure level. But just to prove to you that this is actually Python and not some like intermediate representation thing that compiles to something else, that runs something else, I'll just do a simple, len check. So if the length of this is less than, let's say, 10, I'm just going to return 0.0, right? Kind of a simple example. So I'll actually return early here instead of going through the map. And actually, if I say if n is less than 10. So this should trigger that conditional. And it returned early with the output 0, right? So this applies to loops, while loops, for loops, try, except. Super powerful when you couple it with this idea of infrastructure awareness. The last thing I'll show you here is just stuff that I've run before on my DGX Spark. So I ran a training pipeline using LoRa, or actually QLoRa to be precise. And we can see the workflow here just composed of 3 steps. We have some metrics being shown here. We can see the trace, the model training loss curve here as it ran over time. These are reports, which if you're familiar with Flyte 1, were called Flyte decks. These are just HTML reports that you can publish imperatively in your code. And you can actually define your resources so that this ran on a GPU environment. So here's my training task. Again, this is all just Python with PyTorch installed in here. I can define my task environment separately in a different module so it doesn't clutter your Python logic if you don't want to get confused about it. Then you can import this GPU environment into your workflow script and then decorate this function. Really, all we're doing here is asking for 1 GPU. The only one available on my DGX Spark is the one, the one chip that's on my DGX Spark. And the workflow ran with this full training trace that's available here. The last thing I just want to show off real quick before hopping back into the slides is that you can actually do serving. So if we go to the app section here, we see that I'm serving the small language model that I just trained to perform SQL, natural language to SQL translation. And here I've done some inference to say, convert this natural language query into a SQL query. So you can see that this server is actually running and taking requests. So just to tie it all up, just hopping back here. Effectively, what we've seen is that we're trying to formalize this notion of infrastructure as context. And what does this mean? It means that we've externalized the state. So the run state lives outside the compute layer, the IO, the code, all of the dependencies, they live outside of the compute. And so no single node has to survive for the system to rehydrate and take a workload to completion. Infrastructure as context is the corollary to this, which means that the runtime can see compute resources and can provision them dynamically at runtime itself. Can also introspect into historical runs. So if you have a bunch of agent traces, the system at runtime itself, or maybe out of band, can look at all of your agent traces and see what decisions it made to what effect. The result of this is you can actually implement automatic recovery from both logic bugs and infrastructure failures at runtime. So, oops, that guy. Oh, yeah. Sorry, I'm getting used to this new streaming platform. Okay, so it's pure Python. That's great. We saw the DevX was really nice. It allowed you to get the compute you need for the workloads that need it. But that's not enough for us. The nice outcome of all of this first principles re-architecting of Flyte 1 to 2 is that we get massive speed ups in performance. So we benchmarked Flyte 1 and Flyte 2 on a common configuration cluster with identical configurations. And we found that for many common workflow patterns, Flyte 2 performs up to 6.5 times faster. It's a lot more memory efficient, has a much lower memory footprint, actually has a constant memory footprint under certain conditions, and actually is 1.7 times faster, can hold many more sub-actions, sub-tasks concurrently compared to Flyte 1. And this isn't it. The other thing we cared about is, the other outcome that came out of just working with pure Python or whatever the native programming language is that actually agents can write Flyte 2 code a lot more efficiently. So we found in some of our benchmarks that it was up to 1.78 times more token efficient writing Flyte 2 versus Flyte 1 code. It had a much lower iteration count to a successful run, meaning that your agent didn't have to spin its wheels and expend tokens trying to debug issues, since V2 is just pure Python. And so, as you can see here, there are also a category of things that can only be done in V2 that cannot be done in V1. And speaking of agents, they not only need performance in terms of token efficiency, but also scale. And I'll hand it over now to Ketan to talk about some of the exciting things that we have in Flyte 2 in that regard.
Thank you, Niels. That was fantastic. I will share my screen now. And actually, Niels went over and explained all of the things that we do in Flyte 2. And these are all available in open source and DevBox today. What I'm going to do is I'm going to demo Flyte running on a cluster, but this is running with the Union engine. And one of the things he just said right now, if you remember, he said, it's very fast even with agents. So I'm going to use a very heavy agent. I'm going to use Fable here and ask it to write me a thing. Let's say I want to visualize the iris, this is our machine learning 101, the iris data set using Flyte tasks, and then let it go. It's going to take a little bit and come back. So we'll come back to this in a bit. Till then, what we'll do is we'll see some couple other examples. So in this, I have, Union, Flyte ships with the protocol for reusable containers, and Union ships with the implementation of reusable containers. What reusable containers are like warm pools, because agents need to be fast and need to scale dynamically to machines. Some people thought, initially Flyte was slow because it's running containers and so on. We've re-engineered the core. Data movement happens in Rust. All coordination happens outside in Union, outside of etcd and so on. And there's a core engine that we have built, and things run really fast. So let's run something. I have a fan out, and we can adjust the size of the fan out, and we can instantly launch it. If you'll see, it builds the containers if it doesn't have one, and then launches things. And when we launch, I'm just going over there. It spins up a warm pool of container. If not, it's not there, and it's already done. If you rerun this, because it's a warm pool, it should stay there, and it should, like, instantly complete. And that's running thousands or hundreds, in this case hundreds, and it's pretty fast. Another one usual use case is you are now running a agent. So I actually built an agent, that is, a dummy agent, again, which is going to have an injected failure in out of memory. So let's see how that works. Okay, demo 2, I have that one. So, and I'm going to give it an objective to summarize a corpus. Okay, it's again builds the container. I'm iterating rapidly from my local to remote, and the agent runs. You can see what was the input. You can see the code in the UI live here, as this was the code. If there are any dependencies of the code, they get wrapped up and shown right in here. You see it actually failed the first time, and the failure was out of memory, because if you see, I ran this task with very little memory. It was only 250 megabytes of memory, and maybe loading the corpus took a lot of time. So what it did is caught the error and fixed it and gave it 1 gigabyte of memory. And instantly, nobody had to go and fix it or babysit it. It was able to solve that problem by requesting more memory if needed. And then it continued on, and we got the results. But sometimes you're not that lucky. You don't know the error beforehand, or you don't think about it, or you're not able to catch it. So let's take an example of a long running pipeline. So what I did is I've written another example. I call it a training pipeline, and this will run for a long period of time. And I have actually injected a failure in the evaluation step, and this is just raising the failure. So what we'll see is when it runs, as it's going through things, it's doing the cleaning and embedding, and then after that, it's going to train the model. And this is a synthetic step, so it's pretty fast, and it actually goes to evaluate. But as you saw the code, there was a failure, and it failed. And you'll see the feature loop. It was an infrastructure failure, right? One of the serving holdout systems downstream was for 503. So how do you fix it? So you can fix the code by fixing the code change, right? In this case, my fix is pretty simple. I just comment the exception out, and I rerun it. But if I rerun it, it's again going to fail. And that was actually, I didn't intend to do that, but it's going to fix it. But it's going to rerun the entire thing, right? It's doing everything. I don't want to do that. You can actually, in fact, say, I want to run this with the recover label. And let's go back to the original run. And this was the one that failed, right? You can just take the run ID and say, hey, can you recover from this? Sorry if you cannot see my screen. Can you recover from this and run with the code change? Remember, I changed the code to comment out the things. Oops. Yeah. So if you run this now, what it does, it rehydrates the state from the previous run, and you'll see all of them are complete, recovered already. So there's no output. The outputs are recovered, and then it goes to evaluate with the code change, and the code change is patched in. This makes it extremely durable and recoverable, and you can do various other things, and I'll go through them and explain a couple of different things that you can achieve with this one small feature that exists in the system. Okay, remember that agent that we had run? Oh, it's done. It wrote me this. Of course, it wrote a demo 4. So why don't let's see what is demo 4. So it did some iris visualization stuff, imported matplotlib and everything. So let's run Flyte run demo 4. I don't even know what the structure is. Okay, it's visualize. So you can say, let me run visualize. And by default, it sees that there's no image. And now it's going to build the image dynamically. And it's actually building the image. The remote platform Air Union builds the images remotely, and it built the image rapidly. Now you're back, and it launched the execution. And as the execution runs, you can actually observe the logs of what it was doing, and it's complete. And it printed a report. because it knows about Flyte too. It knows that it can visualize using reports, and it's visualized better than what I could have done. So, and it did it like in a minute, and I didn't have to touch the piece of code. So this is the substrate on which an agent can, or a human can, write code that's durable by construction. All right, let's go back to our slides and give me a holler if you can see it. Can you see it? Okay, awesome. So what did we see? We saw agent writing code, but moreover, we saw warm pools and reusable containers that can rapidly run warm pools. By the way, this warm pool now extends to ray clusters as well. We can keep warm ray clusters and run things on them. So if you're doing that quick iteration, you can go and do that very quickly, and it's available on Union today. Moreover, you also saw durability with infrastructure as context. You were able to handle an error. Most of these infrastructure failures are propagated back up into the system as exceptions in Python or errors in Rust or other languages, and you can figure out what you want to do them and handle them. And finally, you saw recovery. Let's jump into that a little bit. You saw recovery. You saw what I was able to do is take an older run and just fork it and fix the code and deploy it instantly and fix it, right? So we think the same feature can achieve three things. One is recovery. Recovery is when there are external failures and you don't want to redo the work. It's that middle of the night, 2 a.m., and you're just like, oh my God, the downstream service is crashing. Oh, it's back up. Claude was dying. Let's back up. Let's recover. And boom, it will run instantly without redoing the work. Second is fork. Something ran, it failed. Maybe there was a downstream corruption that you created with the data. Because your data was wrong, so you want to fix the data or code, and you want to deploy it again. So that's forking. And then replay. You might want to take the older code. It was successful, but you may want to perform a what-if analysis. Let's say one of your agents did some work, but the outcome was not as expected. Oftentimes, it's very hard to go and change that one small thing within the flow to see how it would have behaved. Now, the fork replay system in V2 enables you to go and modify that part so that you can test different hypotheses, maybe change the system prompt and see how it behaves. And by the way, all of this is done with Python code. No DAGs, no DSLs, no complicated setup, no deployments. You write code and it just instantly goes to production. This is also based on the popular concept that we don't want to build high-level frameworks to solve problems. Build the low-level stuff, and you can bring other frameworks on. And Niels will touch on this in a little bit. And hopefully now you're with me in the definition of durability. Durability is not a one thing. It doesn't mean just go and replay the code. That is one solution, but it needs other things. It needs, we do need code solution. That's the first thing. So we have intra function checkpointing. So intra one task. So you can actually run millions of things within one Python thing, and they are durable. You can run across containers. So that's also available in the system, and you can have retries and different types of retries, queue budgets, and so on. Second is within a run, you can recover from failures. Or you can do across multiple runs, you can use recover and fork. And finally, you can also use caching so that many agents could share or collaborate and share the results across runs. And these are all available in the same platform. And we think this constitutes to be a real durable system. And it's already in production at many, many companies. It's made a lot of difference. Mistral's running their research platform on Union. Toyota is doing more than, has improved their iteration velocity by more than 20x. And Artera brought all their large-scale inferencing on the platform and saved more than 60% in the cost. And with this, I want to hand over to Niels to dive into a couple more new features and give you like the roadmap and video number. Thank you.
Awesome. Thanks, Ketan. Hopping right back in, doing a little tag team here. Cool. So we have too much to show in terms of demos. We didn't want to demo this presentation out. So The next couple of slides, I'm going to go through some of the things we're super excited about. Many of these are already in Flyte 2 open source. Some of these are still in union to be open sourced, and I'll show you the roadmap in a second. The first thing I want to show you is this notion of clustered task environments. This is for workloads that require multiple nodes. Namely, the most common one would be distributed model training for large language models and large deep learning models. So what you're seeing here is a clustered task environment workload where you can see the logs per node. You can see metrics per node as well. And this is all declaratively specified in your code. In this case, we're asking for a 2 nodes. Replicas here is set to 2 of containing 1 L4 GPU each. It supports multiple runtimes. One that ships readily available is the torch run distributed runtime. It does support any arbitrary runtime like Hugging Face's Accelerate or Deep Speed, different frameworks like that. So this allows you to really scale up your workloads to multiple nodes when you need them. So if you're a model producer, how do you build and share artifacts, including models and data sets? So this is our take on artifacts. These were available in V1 of Union, but we actually decided to make this part of the core Flyte V2 system. So as you can see here in this code snippet, we are defining a new artifact based on a Flyte file that we have written into this task's local disk. And we're defining this new artifact that will then be uploaded into the system. In this case, this was a small LM2 135 million instruct model that now we understand the lineage of. We can see what the source action was, what are the downstream triggers and apps that depend on this one artifact. And hinting at that, the next thing that is net new in Flyte 2 is apps and model serving. And so this was really, the motivation here is we're training a bunch of models, we're creating a bunch of data sets, and creating a bunch of artifacts on Flyte. And we're already using Kubernetes, we're already using auto-scaling pods. Why not expose that to create long-running services that don't need to be necessarily durable, but are powered by durable batch workload systems in the back that train the models in the first place. And so what you're seeing here is a Llama CPP app environment that's serving GLM 5.2 GGUF quantized on 4 L40s. And this is all running in the Flyte system natively. So you have your entire stack from your batch workloads, model training, batch inference, as well as online inference, all ready to go. And finally, something I'm super excited to share and I've spent a lot of time thinking about and implementing is agents. And so Ketan alluded to earlier that we don't want to be the nth framework for agents or AI, right? We want to be a runtime where we really provide the orchestration and the compute and durability, and you can bring your own things on top of it from the model training frameworks to the agent frameworks as well. So what you're seeing here is actually Flyte's native agent construct. But if you have an LLM API call with pure Python, you could implement your own agent loop or harness that way. You can bring any of the number of agent frameworks out there, and many of them are in Python. Many of them can run on Flyte. You can add the little @task and @trace decorators that you saw earlier to bring the Flyte level durability into your agents in your existing agent code bases. Okay, so that was the whirlwind tour of all the new stuff we've built. Here are more in our roadmap. And really here, open source has sort of changed post agents and AI, right? Many people go to docs and they ask AI directly. And so what we're really want to do here, and a call to action for the community, is that a lot of these AIs and AI systems are built on open source software. And so we really want this to continue to be an open source community. We want Flyte to be governed and shepherded by not just us, but all of our open source users, be they large organizations to individuals. And so there are three key areas that we're investing in the open source. There's core code and infrastructure, there's SDK, and there are net new things that we're bringing from Union into Flyte. So giving back to the community, namely in the form of artifacts that I showed you earlier. So a lot of these items will be spun up as special interest groups. Please join our Slack community to really kickstart this massive effort. And as you can see here, there's a lot going on that we've planned. And so, yeah, looking forward to having folks join. The last piece before I actually invite a special guest onto the stream is the Flyte upgrade path. So this is a question we get a lot. We've been getting a lot over the last few months. On the left-hand side is Flyte 1. On the right-hand side is Flyte 2. How do you cross that chasm? So in Flyte 1, you have an existing cluster on your existing Kubernetes setup. That you can continue to maintain for mission-critical things that you don't really want to migrate or upgrade just now. And you also have your existing workflows. So our recommended path to get to Flyte 2 on the platform side, on the top layer over there, is you can actually deploy a Flyte 2 cluster on the same exact K8s cluster on a different namespace. We can share details on this, but you can actually use a Flyte deploy agent skill suite that we've developed to deploy this on currently AWS or on a arbitrary kind cluster. All you need is a Postgres provider and a object store provider like R2 or S3 or something like that. And we are also going to ship very soon a set of skills to help you upgrade and maintain that cluster over time as we continue to release improvements in the V2 open source. On the bottom side, you have your existing workflows that you can actually easily migrate thanks to Kevin Su. He did some amazing work with a Flyte migrate package. This does a bunch of magic under the hood that we don't really recommend a lot of people do in their own work, but we've done it for you, where you can actually bring your existing Flyte 1 FlyteKit SDK code with no code changes and run them on the Flyte 2 engine. This is really just so you can get to see how the new Flyte 2 engine works and how the programming model works and how the UI works. Our actual recommended path is to get your Flyte 1 code into a Flyte 2 SDK format, the new SDK. And for that, we have documentation, but also Flyte migrate agent skills. So as we saw earlier, agents are really good at Flyte 2 and translating Flyte 1, which is a subset of Flyte 2. So in other words, Flyte 2 is a strict superset of Flyte 1. There's nothing that you can't do in Flyte 1 that you can't do in Flyte 2. Not sure if I said that right, but basically the translation should be pretty trivial for a lot of these agents. And then finally, we have a bunch of agent skills for the Flyte 2 SDK. And so this allows you to build on our net new stack. So that includes apps, artifacts, and more. And so without further ado, I want to bring on Evan Sadler. I don't know if I can. Yeah, awesome. Hi, Evan. Thank you for joining us.
Thank you for having me.
Yeah. I wanted to spend most of the rest of this time just like chatting through your experience with Flyte 2 so far. I know you were at Union, you've had extensive experience with Flyte 1, and now you're at Dandy. So please take it away and just like tell the folks how your experience is.
Yeah, I have a few slides. I'm just gonna walk through if that sounds good.
Yeah, absolutely.
All right. Let's see. There we go. All right. Can everybody see this? Can everybody hear me?
Yep.
Great. All right. Great. So just wanted to start by talking about Dandy. I have this fun video. Niels, let me know if this doesn't play.
This isn't just
But basically, we're a full-service digital dental lab based in New York. We have a scanner we give to dentists. They'll scan your mouth, and we will build all sorts of dental products from replacement teeth to dentures, and we manufacture them in the US. And ML and AI are a huge part of this, from like generating teeth that look realistic all the way to like monitoring our manufacturing lines. So the plug is done. So that's Dandy. About me, I've mostly been like a ML platform, ML ops engineer. I've worked at a few different companies from Seattle, live in New York, and I started off as a data scientist, not really knowing about infrastructure or CS. Mostly like I use Python in a notebook with what was it, like Matplotlib and all those tools that AI runs for us. But I spent a lot of time like writing data pipelines in Spark and Apache Beam and all that, and then also just like training models with like TensorFlow. And so I was pretty prime candidate for Flyte. I learned about it at HBO Max in 2001. I've used a lot of orchestrators, but like the rapid iteration, time to production, and not thinking about infrastructure, just basically offloading it to the brilliant team at Union has been just like, is really, really great. And at Dandy, we have like 30 MLEs and like 20 plus models in production. The models are like these pretty bespoke, complex 3D models you probably wouldn't see unless you're, doing a specific thing. And we also have a small platform team. And so it was like, let's try Flyte. We were probably one of the first people to use Flyte v2 in open source. We were looking at GitHub, just waiting for the Helm chart to be released. And this is mostly because our existing workflow, our existing code didn't really work with Flyte 1. And so it was kind of a challenge to migrate without rewriting our code. And so like Flyte 2 is dynamic. And so that I'll explain more, but it basically allowed us to migrate like really, really, really quickly and easily. So we use it for training. We use Q for job queuing and quota management. Like if we need to do gang scheduling of RAID jobs or, flex start and all that. And then MLflow for experiment tracking. This is a screenshot with a bunch of redacted jobs. But we have a bunch of projects and, we'll have like, 30 or 40 models training at a time right now. And how do we take advantage of Flyte 2? We basically have a single training workflow that's config driven. And now that Flyte is so is so dynamic, we have a driver node, and within it, we can basically schedule a training job, with different hardware and configurations, and it's all just in Python. And so you can see on the left, we have like the train A2 high GPU 4G. That's just a machine type in GCP. And then we'll add like an X4 or whatnot to be like, multi-nodes. And then, so we're really liking that. I think beyond that, they've touched on this, but the error handling is great. The driver node is just catching infrastructure errors like OMs, and we're just treating it as if it happened in the same, in the task. And that allows us to do things like, eventually maybe start runs with more resources, but really it's like the basic stuff, like cleaning up the state of the ML flow run so it says the job was canceled. These are like things that the machine learning engineers just like tend to notice and the researchers notice. And Flyte 2 makes that very easy. The image builder for V2 is so fast, and whatever magic is happening, we love it. And then on the UI, it's like completely different. We can add custom links to like MLflow and then do mid-task reporting. Basically every task in this list will have some form of report. And one we added recently was like the GPU usage, which you get for free if you use Union. But we've sort of hacked together something, and now we're just kind of building out this training, I guess, pipeline or task with subtasks. But so it's going really, really well so far. I think like there's some fun stuff that Flyte 2 unlocks that are like challenges for us that usually require infrastructure and Flyte makes possible. And so like one thing is scheduling training jobs across regions and hardware configurations. We could do this in a driver, and it's all sort of Python. We can kind of, do things where it's like, hey, we're not getting the like 80 gig A100s. It's taking 3 hours. Let's try something else. Like that flexibility is just something that humans are doing right now, canceling jobs. And it'd be really great to have it happen automatically, or even give like an agent like the opportunity to choose what to do, and then reach out via Slack to a human and make a decision for them. The other thing is like it's all async now, and so we can do some like tasks mid-training, like monitoring resources and potentially canceling jobs if GPUs go idle. Stuff like that we can do with like reporting and Chronosphere and other tools, but like it's just great to have it all in the Flyte workflow, and sort of doing it at the source versus having to export metrics and all that. And that's just like makes us be able to like work fast and add features, and even let folks who aren't on the platform team add features too. Cool. Well, that is mostly it. I just want to say thank you to the Union team. It's a really great piece of software, and it's making us work a lot faster. So we appreciate it.
That's awesome, Evan. Thank you for the presentation. One quick question: what was like the big wow moment for you when because you have background right in Flyte?
Yeah.
Was there a particular moment that you saw this and was like, oh wow, this is actually different?
Oh man, I think it's been, what is it? Let me think. I think like a wow moment here is like right now we use Ray for training, and Ray's great. We use it for data pipelines as well, but for training it adds overhead. You're like running a cluster inside of a Kubernetes cluster, and the logs are different. And so, and it has its own resource specifications. And we were like, hey, let's see if we can switch from Ray to the like default PyTorch plugin for distributed, which is like running Kubeflow. I was able to set that up and just add an if statement in the driver node. And then it's like, we've migrated if people want to. And that is unbelievable. And it would have probably taken, I don't know, a few weeks, and I don't know, it would have just been like a hassle. So that type of flexibility is just incredible.
Nice.
You should try the cluster task, Evan. That's like even more. Yeah.
You can check it out. It's kind of new.
Yeah, and it's so I'm just really happy, and it feels like all the like with the roadmap and things that are coming out, it's like exactly what we're trying to implement ourselves, but you all do it at a league above what I would do on my own. So I really appreciate it.
Awesome. Yeah. Thank you. Thanks so much. And Ketan, can you take us home?
Yeah, like last couple slides, let's quickly do it. You saw a lot of things today, but I wanted to be like, we want to be extremely clear about how we differentiate at Union. Flyte is the open source software that we shepherd, and it's used by lots of amazing companies in the world. You just saw Evan, and there are many others. On the other hand, Union's like the bigger sibling of Flyte. It takes all of Flyte and makes it enterprise grade, more scalable, performant, and of course adds some more features on top. We also, like for example, there were some people like last few days have been running like 250,000 fan out on thousands of GPUs, and it just scales rapidly on the system. And it's designed like that's where we did the engineering in Union. Union is not dependent on Kubernetes for the scheduling and so on aspects, while Flyte is very, very community first, and we built it for people to adopt it rapidly. Our vision is that almost every team in the world should be using Flyte, and you saw how easy it is with Evan. We want to make everything native, and it's a small team. A couple guys together can get everything done within the team. So go try it. And if you need help, we are here. We are here to scale you up, and we are holding your back. So thank you. What you can do today? Flyte is available in DevBox. So pip install Flyte, start the repo if you can, and then you can do Flyte start DevBox. If you have a big GPU box, of course, that's even more fun to use DevBox. Or else you can follow the guides to deploy it on a Kubernetes cluster nearby. And we have a lot of documentation and content. There are skills. There's all kinds of things. Please involve yourself in the community. It's sad to see open source communities die with AI. We don't want to do that. Like the human to human connection is what makes communities possible. So be there, be present, and cheer people on. And the reason for this is like, AI answers all your questions, so you don't end up asking questions to the community members, and the community feels lonely. So come on over, have more chats. Thank you.
Awesome. Yeah, we're at time, so I don't know if we want to do any questions or if there are any actually in the chat.
I think we are over time, actually.
Okay, so, yeah, we are at time.
Thank you,
everyone.